Now, after seeing the evolution of software architecture over time, let's focus on a single application or system and check how its architecture could evolve over time. In other words, we will check the architecture of a system before implementation, which is known as prescriptive architecture, and after implementation, which is known as descriptive architecture. While prescriptive architecture is created before implementation and serves as a guide, descriptive architecture is derived from the implemented system itself. It represents the actual architecture that has been realized through the development process. Prescriptive architecture refers to an architectural approach that provides guidelines, rules, and best practices for designing and implementing a software system. It is typically documented by software architects and serves as a blueprint or a set of instructions for developers to follow. It includes the choice of architectural patterns, technologies, and frameworks. However, prescriptive architecture does not guarantee that the implemented system will perfectly match the prescribed design. Descriptive architecture, also known as realized architecture or as built architecture, refers to the actual implemented architecture of a software system. It represents the real structure, components, and interactions of the system as it exists in practice. It's derived from the implemented code base and the system's runtime behavior. Descriptive architecture can be determined through code analysis, reverse engineering, documentation, and system observation. It aims to capture the current state of the system and provide an accurate representation of its architecture. It may include diagrams, documentation, and other artifacts that describe the implemented system. This illustration gives us a side-by-side comparison of two architectural models of the Linux kernel, prescriptive and descriptive. It visually represents the theoretical versus practical arrangements of key components within the Linux operating system core. On the left, we have the prescriptive architecture, which shows the planned idealized structure of the Linux kernel. This diagram is akin to an architect's blueprint. It represents an orderly layout with components like memory manager, process scheduler, file system, network interface, inter-process communications, and library. These are connected through a series of arrows indicating the flow of information and control, suggesting a well thought out design intended for implementation. On the right, there is the descriptive architecture, which details the actualized or as built layout that has come to be through development and use. This diagram might appear more chaotic with numerous additional connections and pathways that were not evident in the prescriptive plan. This reflects the complexities and adaptations that occur during the real-world execution, maintenance, and evolution of the system. Both architectures serve different but complementary purposes. The prescriptive side guides developers on how the system should be built, while the descriptive side reflects how the system actually functions. The contrast between the two can be significant, as the realities of software development often diverge from initial plan due to various constraints, optimization, and practical adjustments. In essence, this illustration captures the dynamic nature of software architecture, especially in complex, evolving systems like the Linux kernel. It is a candid acknowledgement that while the prescriptive architecture provides the foundation, the descriptive architecture represents the living, breathing entity that is the Linux kernel in action. Here we see an illustration of an AWS cloud environment I've generated with CloudMapper for a real-world application that has thousands of users and receives thousands of QPS or queries per second. It's a form of a descriptive architecture. If you want to elevate your AWS game and looking for more insights on how to craft such a diagram, swing to my YouTube channel and check my video visualizing your AWS environment, how to use CloudMapper to generate diagrams. This diagram depicts the intricate and complex network topologies of an AWS cloud environment by showing how AWS services are interconnected within an account. It's a spiderweb of nodes and connections. Each node represents a different AWS resource, such as EC2 instances or Elastic Compute Cloud, RDS or Relational Database Service, including their subnets and security groups, Simple Storage Service, or S3 buckets along with their public and private status, VPCs, Virtual Private Cloud, subnets, route tables, Internet gateways, NAT gateways, and VPC peering connections. Route 53, DNS configurations and how they relate to other resources, AWS Lambda, along with their triggers from other AWS services, Amazon CloudFront, distributions and their connection to S3 buckets or other origins, AWS EAM, or Identity and Access Management, which is a visualization of roles and their relationships to other services. We can find also DynamoDB tables and their connections, Elastic Load Balancing or ELB, both Elastic and application load balancers, Amazon ECS or Elastic Container Service, and EKS, Elastic Kubernetes Service, container services and how they are deployed within the infrastructure, AWS CloudFormation, stacks and their resources illustrating how they are interconnected. We can also find AWS autoscaling groups and their associated instances. The lines between these AWS resources and services illustrate the communication paths, dependencies, and interactions, which are the lifelines of the cloud ecosystem. The clusters of nodes indicate tightly coupled systems or services that heavily interact with each other, possibly representing individual microservices, applications, or storage clusters within the environment. This cloud suggests areas of high traffic, complex interdependencies, or critical points of the architecture that require robust fault tolerance and high availability strategies. The myriad connections branching out from these clusters could be various API calls, data transfer activities, or other inter-service communications necessary for the distributed system's operations. Some nodes seem to be more central to the network, indicating core services that might be integral to the cloud environment's functionality. In contrast to the clear and orderly diagrams often seen in architectural blueprints, this image conveys the real-world complexity and dynamic nature of cloud-based infrastructures. They serve as a testament to the power and flexibility of AWS services capable of supporting a diverse range of applications and varying scalability, reliability, and security requirements. Such visualizations are not only valuable to understanding the current state of the system, but also essential for planning future changes, identifying potential risks, and ensuring efficient operation of the cloud environment. They translate the abstract and often intangible nature of cloud computing into a tangible representation, enabling stakeholders to grasp the comprehensive view of their system's architecture. I won't go deeper in this case study because we've reached now the borderline between software architecture and system architecture. This illustration sits actually at the intersection of software architecture and system architecture. Excited about diving deeper into the world of software architecture? This video is just the beginning. Check out my Udemy video course on software architecture, where I explore these concepts further and dive into real-world challenges. The link to the course is in the video description below. And here is a bonus. Subscribe to my newsletter and you will get free access to all my courses. If you found this video helpful, don't forget to hit the like button and subscribe to the channel for more updates and tech insights. See you next time.